In this lecture, we will consider the generalized linear model. The generalized linear model is an extension of the general linear model. The general linear model included the multiple linear regression model. For multiple linear regression, we had that the response variable yi of observation I equals a vector of possible covariates observed times the parameter beta, which is also a vector, plus a error term I. And that was for the observations I, which goes from 1 all the way to observation n. The generalized linear model extends this model by relaxing the assumptions which we had on the error term. Let's just quickly remind ourselves what those assumptions were. For the general model or for multiple linear regression, we assume that epsilon I is independent for all pairwise observations. We also assume that it comes from a normal distribution with expected value 0 and a variance sigma square, and that these variances were constant over the range of possible values for the covariates. The generalized linear model actually relaxed these assumptions by only assuming that the error term comes from the exponential family of possible distributions. We will consider this a little bit more in detail in these slides. Before we define the generalized linear model, we need to revisit the exponential family of distributions. We saw in the second here that the normal distribution is in the exponential family. We also saw that the Poisson, the Bernoulli, and all these other distributions are members of the exponential family. It's interesting to note that the normal is a continuous distribution, as the gamma distribution is a continuous distribution. But the Poisson and the Bernoulli and the binomial is not continuous. So very interesting is that this exponential family actually includes continuous distribution functions as well as discrete mass functions or probability mass functions. After we've spent time on studying the exponential family, we will carry on and define the generalized linear model. We will consider aspects like the different components of a generalized linear model, how to fit the model, and then we will also consider the concept of deviance, which will be used to select the better models as we compare different models for a data set. Thereafter, we'll define the residuals, which we can use then to check the feasibility of the specific models. Any distribution of whom the density function or probability mass function can be written in this form is considered to be a member of the exponential family. We will see just now how we can rewrite the normal density function to be of this form. We will also see how we can write the Poisson probability mass function in this form. Theta is known as the natural parameter of the exponential family, also called the canonical parameter, and we will see that the expected value of the random vector is actually a function of this natural parameter theta. The parameter psi is the scale parameter. So we see here we have a function a of the scale parameter. We have here a function of the scale parameter and the random variable y. And here we only have a function of the parameter theta. We start off here with a product between the random vector and the parameter theta. These functions need to be identified when we need to prove that a distribution is in the exponential family of distributions. Let's consider the normal distribution, and specifically the normal distribution with expected value mu and sigma square. We know that the density function is given by this expression. If we develop the quadratic form, we obtain the value over here. And if we put the constant value to the power of e, we can get that expression over here. Combining the different terms, we can simplify the expression to be in this form. Please check the detailed algebraic steps for yourself. If we compare this expression now with the expression of the exponential family, we will be able to identify the different components of the exponential family. Comparing this form of the density function of the normal distribution with the general form of the density function of an exponential distribution, we can identify the corresponding components and therefore show that the normal distribution is a member of the exponential family. By doing this comparison, we see that theta equals mu. We also see that b of theta equals a half mu square. We also see that a of psi equals sigma square, which is the scale parameter. The function a is the identity function. This term over here is then c of y and theta. Therefore, because we identified the different components, we can conclude that the normal distribution is a member of the exponential family. We can also write the probability mass function of the Poisson distribution to be in the form of that of the exponential family. Starting with the mass function of the Poisson distribution, we can write that to be equal to e to the power of y, the ln or the log of mu, minus mu minus the ln or the log of y factorial. Comparing this now with the general form of the exponential family, we can identify the different components as follows. We see that theta is equal to the log or the ln of mu. We see that b of theta equals mu, which is equal to e to the power of theta. Also, the scale parameter is equal to 1. Therefore, a of the scale parameter is also equal to 1. C of y, the data, and the scale parameter is equal to minus the log of y factorial. Therefore, we can conclude that the Poisson distribution is a member of the exponential family of distributions. The Bernoulli distribution is also a member of the exponential family. Please check the notes, page 70, for the detailed calculations showing that the Bernoulli distribution is a member. Clearly indicated there is the different components. Theta equals beta, theta equals, as well as you need to identify what A of the scale parameter is, as well as what the function y, C of y and the scale parameter is equal to. The details are given on page 70. Please consider that. The details of showing that the binomial distribution is a member of the exponential family is given on page 71 of the notes. Please work through that and identify the different components to prove that the binomial distribution is a member of the exponential family. Also consider page 72 of the note showing that the exponential distribution is a member of the exponential family. The gamma distribution is also a member of the exponential family. The detailed calculations can be found on page 72 of the notes. Please identify the different components to put it in the general form of the exponential family and therefore conclude that the gamma distribution is a member of the exponential family. For the exponential family, we have the following results. The expected value of a random variable, which is a member of the exponential family, is given by the derivative of the function b in the value of theta. The variance is given by the function a of the scale parameter times the second order derivative of the function b in the value theta. The proof of these results are given on page 68 of the notes. It will not be required from you to be able to prove these results in the exam or in a test. For the normal distribution, you will remember that we had that b of theta equals a half mu square. So we can easily, using the results from this theorem 26 to calculate the expected value of a normal distribution, which is going to be equal to a half to mu, which is just mu. The variance of this random variable which follows a normal distribution will be a, the scalar parameter, times the second order derivative in the value of theta, and we saw that a of the scalar parameter is just equal to sigma square in the normal distribution, and the second derivative will only be equal to 1. So the variance of the random variable y is just sigma square, using this result from theorem 26. Please consider the notes for calculating the expected value of a Poisson distribution and the variance of a Poisson distribution using this theorem 26. Other distributions are also considered in the notes. Let's define the generalized linear model now? The generalized linear model is defined through three components. The first component of the generalized linear model is the random component. It is the random variable y, which is the response variable, which we assume is a member of the exponential family. The second component is what is called the systematic component, or also the linear predictor, and that is the linear function of the covariates. For example, if we have a covariate x1 and x2, eta, the linear predictor, is given, for example, by that linear combination or linear function. Here's another example of a linear function which includes an interaction term. So that is the second component defining the generalized linear model, the systematic or linear predictor. The third component is the link function. And it's through the link function where the generalization of the general linear model to the generalized linear model really takes place. It says that we set the expected value of the random variable y, the expected value of the response variable equal to mu. We set that equal to the linear predictor through the link function. Very important is this expression over here. We can also write it as the expected value of y, taking the link function of that expected value is then equal to the linear predictor, which might be, for example, as from the second component be beta naught plus beta 1 x1 plus beta 2 x2. We can summarize the generalized linear model through the three components, which defines the linear model as follows. Y is the random component, the response variable, which is a member of the exponential family. The distribution of y then is a member of the exponential family. Also, we have the linear predictor eta, which is a linear function of the explanatory variables. For example, beta naught plus beta 1 x1 plus beta 2 x2 if we have two explanatory variables. The linear predictor is linked to y through the expectation value of y. Thus, the expected value of y is linked to the linear predictor eta through the link function. So the link function of the expected value of y equals the linear predictor, which in this example is equal to beta naught beta 1 x1 plus beta 2 x2. It's specifically the link function which makes the generalization of the general linear model possible to the generalized linear model. This generalization is very powerful because we also extend the random components distribution to the broader class of exponential family distributions. In the next lecture, we will see how we can fit these type of models to a data set and how we can interpret the results from such a model fitted to the data. Furthermore, it's also important to note that the observations are independent. The response variable observation y1 is independent from the response observation y2 all the way to yn, the nth observation. All these observations on the response variables are independent. Also, the response variable can take on any distribution from the exponential family. And there's no requirement that it must be normal, as in the case for the multiple linear regression. The normal distribution is included in the exponential family. Therefore, multiple linear regression is a special case of generalized linear models.